Today we're going to talk about states of matter and phase changes. Now I put this lesson in my energy unit because turns out depending on what state of matter you are in, whether a solid, a liquid, or a gas, you're going to have different energy characteristics. Also, as you can imagine, going through a phase change, meaning solid to liquid to gas or gas to liquid to solid, that's probably going to involve some sort of a change in energy for these phase changes to happen. You're probably going to hear some of the same terms that I've been using this unit so far, like exothermic and endothermic and releasing heat and absorbing heat and a positive and a negative, all of that stuff that really wraps this unit up into a nice little present with a bow on top. So let's get into it with our states of matter and phase changes. Okay, a review of our 3 states of matter, and we are not talking about plasmas because we are not super scientists yet. We are 10th grade chemistry students, and that is just fine. So we have 3 states of matter. The first state of matter is a solid, the second state of matter is a liquid, and the third state of matter is a gas. By definition, matter is anything that has mass and takes up space. Okay, volume is the term to represent the space that matter makes up. Now, everything can be categorized into these 3 states of matter. Now, let's look at what we have to say about solids here. In solids, as you can see, particles are tightly packed together in a fixed arrangement. The particles can vibrate, but they're not going to move. Now, liquids, the particles are still pretty close together, but there's no distinct arrangement. That's why liquids can take the shape of whatever container they're in. Particles can move and slide around each other in a liquid state. And then finally, my gases, their particles are free-floating with no distinct arrangement, and the particles move and collide with each other. Like I've mentioned before, our entire next unit is strictly focusing on the gaseous state of matter because, as you can tell by this picture, it looks like there's a little bit more creativity for movement and energy, which, yes, there is. Okay. This is also hopefully a review of the phase changes. Matter can change its phase when it experiences a change in temperature and or in pressure. So here I'm looking at 2 things that help change what state of matter I am in: temperature and pressure. Well, pressure affects the ability of the particles to move. If I apply pressure onto a sample of matter, I'm allowing it to increase or compress, right? And then if I'm compressing matter down, it's probably not going to move very well, right? Temperature now, it affects the kinetic energy of the particles. As we can remember, temperature is a measure of the average kinetic energy. So if I know if I increase the temperature, I'm going to increase the kinetic energy of the particles, the motion of the particles. From the previous slide, we saw that there is a difference depending on whether I'm solid, liquid, or gas on how much motion these particles can have. So that is important when it comes to phase changes. That was a lot of talking. Okay. So let's look at this phase change diagram. It's a cute little triangle. So going from my solid phase to my liquid phase, that process is called melting. Going from a liquid to a gas, that's called vaporization. You will probably also see or hear boiling to represent that phase change. We tend to use vaporization or evaporation or boiling kind of interchangeably. Technically, evaporation and boiling do not mean exactly the same thing, but we are not super scientists yet. We are just 10th grade chemistry students, but for our purposes, they are the same thing. That is the phase change from liquid to gas. Then if I have gas going down, let's go back to the liquid state. So having a gas turn back into a liquid is condensation, and a liquid turning into a solid is freezing. Those are the most common 4 phase change terms. Now, sometimes if I have specific temperatures and pressures, which we mentioned, temperature and pressure is what gets matter to change phase. If I'm under specific temperatures and pressure, I can sometimes get a solid to turn into a gas. That process is called sublimation. And I can also sometimes get a gas to turn directly into a solid, and that process is called deposition. So these are the 6 terms for our phase changes of matter that we can do. Okay, so I talked about pressure and temperature affecting these phase change. Let's look at some graphs. This is called a phase diagram graph. A phase diagram shows what phase a substance exists at certain pressures and temperature. So let's just unpack what we are seeing here today. Along the x-axis, I am measuring temperature in degrees Celsius. So as I move along the x-axis this way, I see temperature increasing. My y-axis, its measurement is in pressure, in millimeters of mercury. That's one of the units that we measure pressure in. I know it's wackadoo. We'll get to pressure units next unit. So as I move up the y-axis, I see an increase in pressure. So since state of matter determines on what temperature and pressure you're in, I'm noticing on this graph there's like a solid section, a liquid section, and a gas section. There's also some lines that are the boundaries between those. So those lines are phase boundaries that show where the phase changes occur. Okay, so now the key thing about these phase change diagrams is the phase change diagram for water is going to look different than the phase change diagram for like carbon dioxide. It's going to look different than for ammonia. It's going to look different depending on what substance you are, okay? But they all kind of have this same similar shape where you have a solid section and then you have a liquid section, and in this entire kind of bottom part of the graph is going to be your gaseous section. Okay, let's really unpack what a phase diagram of water would look like. And we're going to actually, write some things on our phase diagram of water in our notes handout today, because there's a lot going on here, and you will be expected to, if given a phase diagram, indicate some of these important parts and tell me what they mean. Okay. The first thing that is hopefully the most easiest for you to identify is which sections the solid occurs in, the liquid occurs in, and then the vapor or the gas occurs in. I could potentially give you a temperature and a pressure and expect for you to map those together and tell me, well, what state of matter that substance would be if it was at those temperatures and pressures. That is a possibility for y'all for sure. Let's talk about these lines, these phase boundary lines. Y'all, I can represent the phase change terms, the 6 terms that we reviewed on this phase change diagram, or on this phase diagram, right? If I am moving across this line, going from a solid to a liquid, well, that's melting. That's melting doing that. If I'm going the opposite way, moving from the liquid section to the solid section, that's freezing. Look at us now. If I am moving from the liquid section over to the gas section or the vapor section, that's vaporization, and condensation would be moving the opposite way across that line. Now, the deposition and sublimation, meaning the solid to gas and gas to solid, they're a little bit sneakier, usually in a very small area for you to have to look at. So sublimation, once again, is going from a solid to a gas, and deposition is going from a gas to a solid. The way I remember the difference between sublimation and deposition, because those to me are the most confusing terms. Sublimation, it starts with an S. So when I think sublimation, I think going up to the sky, like typically a gas would do if it turns from a solid into a gas. So sublimation, right? And if I think of deposition, that's where you go from a gas to a solid. I think deposition starts with a D, so I'm going down, or I'm being deposited down. That's what helps me. Hopefully that may help you a little bit. Cool. So what else can we interpret here from this phase diagram? Very important. You need to be able to point out what the melting point is of a substance looking at its phase diagram. Well, what is the melting point? You will oftentimes see me abbreviate melting point as MP. Not only me abbreviate, most scientists do this. MP. By definition, the melting point is the temperature at 1 atmosphere, and an atmosphere is a pressure unit. So at 1 atmosphere of pressure, at which matter will melt and or freeze. Okay, so you're like, okay, how do I find that on my graph here? Well, the way that you find this on your graph is you first find whatever that pressure is, that 1 atmosphere of pressure on your y-axis. There he is. That 1 atmosphere of pressure is important, and we go to the 1 atmosphere because it's what's known in science as a standard pressure, okay? So we're looking at my 1 atmosphere. So this is standard normal pressure, like as if you were on sea level, right? Okay, now I'm like, okay, at what temperature does my substance hit that line that separates a solid and a liquid? That indicates where you will melt and freeze. So at what temperature does it hit that line from 1 atmosphere? So you just do this little dot, 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 dot. boom, I've hit my line. What temperature is that? And you will figure out what the melting point is. The melting point is not a point. It is not like your direction, that one, this one. It is a number. It is a temperature number. So the melting point is a temperature. That dotted line hits this line dividing my solids and my liquids at 1 atmosphere. That was a lot of talking, but we're going to learn how to read some graphs today. So for water, hopefully it makes sense that the melting point for water is 0 degrees Celsius. Typically, you guys would think, well, I thought water freezes at 0 degrees Celsius. Yes, it also melts at 0 degrees Celsius. If it was in ice and I increased its temperature to 0 degrees Celsius, then it's going to melt and begin to turn into a liquid at temperatures higher than that. And so some of y'all are probably like, why don't we call this a freezing point? Well, I don't know. I don't make the rules. But melting point represents the temperature at which that substance could possibly melt and freeze. Amazing. There is some other point for us to find on this graph. Let's see. A boiling point. Now, it's the temperature at the same 1 atmosphere of pressure, that same 1 atmosphere standard pressure at which your matter will evaporate or condense. So here I'm looking at, well, at what temperature at 1 pressure or 1 atmosphere of pressure does it hit this line that divides my liquid and my gas phase? Oh, we hit it here. What temperature was that? I know this is a weird representation of 100. It looks like it almost has like a dot in between there. I don't know what was going on here with this picture. But my boiling point of water is 100 degrees Celsius. That's the temperature at which not only that state of matter will boil, but also potentially would condense back down. Okay, so now we know how to pick out a melting point and we know how to pick out a boiling point. Those are the temperatures at which those phase changes occur at standard pressure of 1 atmosphere, which is real fun. Okay, now here we get into the weird stuff, the real weird stuff. I have something already labeled for me on this graph called a triple point. A triple point is the exact temperature and exact pressure at which all three, I'm saying solid, liquid, and gas, can exist. You're like, there is no way. There is, but it has to be a specific temperature and a specific pressure, and it is usually not a convenient or a common temperature and pressure that we are likely to see just existing in the world. Okay, so looking at this, it looks like for water specifically to exist in all 3 phases, you're going to have a temperature of about a little bit above freezing, right? A little bit above, we would say, the melting point, right? And then we would say it's like, oh my gosh, that's a really, really, really low pressure. So let's kind of visualize and watch a video about what a triple point really looks like in action. So that is way cool, the triple point. As you can imagine, or as you saw in the video, you have to have creating a triple point usually in a vacuum chamber where you can directly control the pressure and the temperature to get to that triple point. But very, 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 very cool. Okay, another cool point to look at here is the critical point. The critical point is at the tippity top of your graph here, and it is the maximum temperature and pressure at which a liquid and gas phase can coexist. That just means that that's the maximum point to where there are distinguishable differences between my liquid and my gas phase, okay? Past that critical point, there is like nothing to distinguish the difference between a liquid and a gas. You're like, well, what does that even mean? We would call something past the critical point a supercritical fluid. So let's watch what a supercritical fluid, specifically for carbon dioxide, would look like past its critical point.
With pressure and temperature that exceed the critical values, the substance will become supercritical and the differences between the liquid and the gas phase disappear. Let's see how this works in practice. For this experiment, we made our own pressure tank. It has a thermometer, a pressure meter, and a pressure relief valve. We also have some dry ice, which is carbon dioxide in the solid phase, a heating plate, and a heating base. We put some dry ice into the tank and seal the tank. As the pressure tank is completely sealed, the pressure builds. The dry ice starts at a low temperature, but with the rising pressure, it soon turns into a saturated liquid vapor mixture at about 40 bar and 5 degrees Celsius. By applying heat to the tank, we increase the pressure and temperature towards the critical point at constant volume. CO2 has a critical temperature of 31.25 degrees Celsius and a critical absolute pressure of 73.9 bar. So we want to heat up the carbon dioxide to its critical temperature, and because the volume of the tank is constant, we can also build up the pressure. As the pressure and temperature reach the critical point, the distinction between the liquid and gaseous carbon dioxide becomes less visible and eventually disappears. The phase boundary between the liquid and the gas vanishes. The CO2 is now in a supercritical state. To return to a state below the critical point, we will cool the carbon dioxide and make it reappear in the saturated liquid vapor mixture. By removing the heating plate and then adding dry ice on the aluminum cylinder, we can observe that the liquid vapor interface suddenly reappears as the temperature decreases. We have returned to the saturated liquid vapor mixture. Supercritical CO2 is used in a variety of applications, for example, to remove caffeine from coffee beans.
Super cool. So once again, you have to create these special point scenarios like a critical point and a triple point in a vacuum sealed chamber to where you can directly control the temperature and the pressure while maintaining a constant volume. Amazing. Okay, so the thing here to kind of really take home is why is the solid over here and why is the liquid here and why is the gas here? Well, solids like to exist at typically high pressures and lower temperatures, right? We don't see a solid that goes past this point right here, okay? Well, that makes sense for a solid because we know that high pressure means you're going to be packed together. That's what solids like. And low temperatures probably going to mean you're not moving around so much. That's why solids only vibrate in their fixed positions. See, some of this science stuff makes sense. Well, what does that say about gases? Okay, well, gases typically like to exist at these lower pressures, right? And much higher temperatures. Well, why? A low pressure means they're not going to be compressed quite as much together. Well, gas particles like to spread apart, right? And at high temperatures, that's a high average kinetic energy, which, gases like to move around really quickly. See, this stuff makes sense. We love this so much. So I'm using some terms like moving and whatever. This brings us to the kinetic molecular theory and what that has to do with the states of matter. You're like, oh my gosh, kinetic molecular theory, all these scary science terms. That's really not that scary. Let's see.
The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving. These particles hold kinetic energy and move around in random directions. In higher temperatures, the particles have high energy, and in low temperatures, the particles have less energy. The more energy a particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern because the energy is low and the particles are tightly packed. In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are put in. In gases like steam, the particles have the most energy. These particles are sparse and move around freely. Gases are usually invisible to the eye and they can be expanded and compressed in different pressures. All matter is composed of atoms and molecules that are always moving. The higher the temperature, the more energy these particles have. And that is the kinetic molecular theory.
Well, that doesn't seem too scary or complicated. Yeah, it's actually not. The kinetic molecular theory just states that all matter is composed of particles that are always in motion in some way. I like to abbreviate the kinetic molecular theory, since that's a lot of words and syllables, is the KMT. So if you hear me say KMT, I'm talking about just the idea that all matter is in motion. So this theory can be used to describe the behavior of my solids, liquids, and my gases. Well, yeah, they all move in some way. Solids vibrate in those fixed positions. Liquids slide and flow past each other, and gases move rapidly and randomly, very, very far apart. Very, very cool. Okay, now the key thing here is there are two things that determine the state of matter and the resulting physical properties that that state of matter has. The first thing that helps to determine whether you're a solid, liquid, or a gas is the kinetic energy of the particles, or the speed and freedom of movement. That makes sense, right? We know solids, they don't have much kinetic energy, versus gases, they move in a lot, high kinetic energy. So yeah, how much kinetic energy something has will help determine what state of matter you're in. The second thing that can also help determine the state of matter is the forces of attraction between the particles themselves. I like to call this the glue that holds the particle together. You're like, she's telling me there's glue in between these particles. There's not really glue. But there is, for all particles, there are going to be some slight forces of attraction that are going to try to pull these particles together. You were like magnets? Yeah, kind of like magnets. Do you remember way back when we learned about how to draw Lewis dot structures and name Vesper shapes? We also talked about polarity, and we talked about some molecules being polar and nonpolar and having like a negative end and a positive end. Well, that's the type of stuff when I'm talking about forces of attraction. There are some kind of like magnetic attractions between particles. Now, depending on what the particle is and how close together they are, the strength of that force of attraction is going to be slightly different. But that plays a big key component on the ability for these particles to want to stick close together like they would do in a solid, or want to spread apart like they would want to do in a gas. And we have an entire lesson next time on forces of attraction and intermolecular forces for you guys to look forward to. Okay, but these two things, how fast we're moving and if there's stuff trying to attract them together. Okay. So on my little graph here, a picture comparison of a solid, a liquid, and a gas. On my solid section, we're going to say that they have low movement. And by definition, if they got low movement, they're going to have low kinetic energy. Also, that's going to mean my solids typically have strong forces of attraction wanting to keep them together. Now moving to my other end on my gases over here, we say that they have high movement, right? Well, they got high movement, they got high kinetic energy. And they have weak forces of attraction, meaning they are not trying to be pulled together to get closer, right? They're moving far apart, or have the ability to move far apart with ease. Very cool. Okay. Now, what does this mean? So we were looking at the solids, liquids, and gases kind of independently, but we know that matter has the ability to change phase, right? Well, since solids, liquids, and gases are different in terms of their average kinetic energy of their particles, all phase changes require a significant change in energy to overcome those forces of attraction that will want to hold the particles together and alter how the particles move. Okay? Now, some phase changes involve a release of energy, and some phase changes require an absorption of energy. Let's see. So how do we get a substance to change from a solid to a liquid to a gas? I put a picture of boiling water on here because I think you probably know the answer. Changing the phase of matter is all about changing the kinetic energy of the particles. So changes in the kinetic energy are observed by us as changes in temperature, because temperature is, by definition, the average kinetic energy of a sample of matter, right? So I can add heat to increase the kinetic energy of the particles, right? And that will help the particles overcome these forces of attraction holding them together. This causes matter to change phase from a solid to a liquid to a gas. It makes sense that if I'm heating something up, I'm increasing its kinetic energy, which means it's going to move much more fast, to where those forces of attraction are not going to be able to contain and hold particles together. See, a lot of this kind of is working together to give us the same result, which is fun. All right, so let's, we said we can add heat to increase the kinetic energy to change the sample of matter from one phase to another. Here we have a heating curve. You have a giant heating curve on the back of your notes page. You better get ready to write down a bunch of stuff on your heating curve when we get to it. But a heating curve is a graph that shows, oh my gosh, look, the temperature of a substance plotted against the amount of heat or energy it has absorbed over time. Okay, so I'm looking at this. I've got, as I'm adding heat to my system here or to my substance, I'm noticing a temperature change, typically going up. In fact, always going up, because heat added will help increase the average kinetic energy of matter, which we will see as a raise in temperature. So heating curves of different substances may look slightly different, like, where they are on the temperature scale and how slopey slope some of these slopes look. But however, they all have this same general similar shape where I have a jaggedy slope up in this direction. That's so not sciencey. Jaggedy slope up. Oh my gosh. Okay. So here's the heating curve that you guys have on your notes. We are going to unpack all of this, but first we're going to check something out that helps summarize what we're about to get into with our discussion on this heating curve.
If we heat a sample of ice, it will melt to water. With further heating, the water will boil to steam. But what's happening at the molecular level during these processes? If we could zoom up on ice, we'd see these water molecules vibrating in a hexagonal crystal structure. The molecules are held in position by attractive forces called hydrogen bonds, but the molecules' vibrations give them kinetic energy. And the temperature of the ice is a measure of the average kinetic energy of these molecules. With the temperature below 0 degrees Celsius, the molecules don't have enough energy to break free from the hydrogen bonds. As heat is absorbed, they vibrate more quickly, gaining kinetic energy, and so the temperature increases. At 0 degrees Celsius, the ice melts as the molecules have enough energy to break free from the solid structure and enter the liquid state. During melting, the temperature remains constant because the heat is used to overcome the hydrogen bonds instead of speeding up the molecules. In the liquid state, the hydrogen bonds are being formed and broken as molecules slide past each other. Under 100 degrees Celsius, they don't have enough energy to break free of the attraction of nearby molecules. As more heat is absorbed, the molecules move faster, gaining kinetic energy, and so increasing the temperature. At 100 degrees Celsius, the water boils as the molecules have gained sufficient energy to break free. During boiling, the temperature remains constant because heat is used to overcome the hydrogen bonds instead of speeding up the molecules. In the gaseous state, the water molecules are free from the attraction of other molecules. Further heating increases the molecule speed and so increases the steam's temperature. The heating curve of water shows the changes in temperature as heat energy is absorbed over time. The sloping lines show when the temperature of the ice, water, or steam is steadily increasing. The flat lines show when the temperature is constant during a state change. When the ice is heating, we see the temperature steadily increasing towards 0 degrees Celsius. As the ice is melting, we see the temperature remains constant at 0 degrees Celsius. This short section of the graph shows that little heat is required to melt ice into water. When the water is heating, we see the temperature steadily increasing towards 100 degrees Celsius. As the water is boiling, the temperature remains constant at 100 degrees Celsius. This longer section of the graph shows that a relatively large amount of heat is required to boil water into steam. At this point, further heat will increase the temperature of the steam.
Now that gives you the general gist of what is happening throughout the heating curve process. We're going to unpack kind of the important points here in a second. But the first thing I actually want to make sure that y'all do is to maybe add the unit joules on your x-axis for heat, okay? Because we're gonna, be scientists here, and we want those actually to these measurements to have units, because that means something. Same thing over here for temperature. Go ahead and pump out a degrees Celsius over there. And then you may also label this heating curve specifically for water. So you could say this is heating curve for water up at the top of your graph. Okay, so I can find some really interesting things real quick on this heating curve. I can ask for you to tell me what the boiling point and what the melting point is, depending on just looking at a heating curve. Once again, the temperature at which vaporization and condensation occurs is the boiling point, okay? So y'all, we said the phase change vaporizing and condensing is that plateau up here, okay? Well, all I have to do is figure out what the temperature is to get to that plateau, and boom, that is your boiling point. Once again, a boiling point is a number. It is a temperature number. So for water, it is 100 degrees Celsius. Now, the temperature at which melting and freezing occurs is my melting point. Well, this plateau down here is where the states of matter either melt or freeze. Oh, all I have to do is figure out, well, what temperature does that happen? Boom, that's my melting point. Okay, so for water, the melting point is going to be 0 degrees Celsius. So those plateaus on my heating curve let me know what the melting point and the boiling point is. So some really important information can be seen immediately from these heating curves. And as you can imagine, different substances are going to have different melting point and boiling points. So this is one of the distinguishing factors on why different substances' heating curves could look different, is where those plateaus occur. Okay, now I want to talk about the slopity slopes, the diagonal line, or the diagonal lines. What is going on here? So notice that the diagonal slopes, where the temperature changes in response to heat being absorbed. This only happens when a substance is within a phase of matter, meaning it is a solid, or it is a liquid, or it is a gas, okay? If I'm a solid, a liquid, or a gas and not going through a phase change, this means that kinetic energy is the thing that is changing within my phases. I can actually visually see this on a graph. We know that temperature is the measure of the average kinetic energy of a substance, right? Well, the only places on this graph where I see temperature changing, meaning something is going up in the vertical direction, is on these slopity slopes, right? So solids, their kinetic energy is changing if I'm adding heat to it. Okay, once I hit the phase change mark, y'all, kinetic energy is not changing. How do I know? Because nothing is moving up on that vertical axis. Temperature stays the same. Okay, but then when I get to liquid, oh my gosh, and add more heat, it's going to increase its kinetic energy, and it stops when it gets to the phase change because no temperature is changing. And then I get to gas, the kinetic energy is changing because the temperature is changing. Lots of words. So that slopity slope means something important. It indicates temperature is changing with that process. So kinetic energy of the particles are changing during within those specific phases. Well, what is going on during the phase changes? These are my plateaus. Notice the two plateaus where temperature does not change in response to heat still being absorbed. This only happens during a phase change. This means only the potential energy of the particles changes during a phase change. All absorbed energy is used to rearrange the particles in preparation for the phase change, not for movement. Now, this is actually wackadoo if you sit and think about it hard enough, okay? If you want to think about it this way, if I get a block of solid ice from my freezer and let it sit on the countertop and wait for it to melt, the second it starts melting until the end when all of it has melted, it will not change its temperature to anything else but 0. You're like, really? Yes. Okay. Because what's happening here is during this process, even though heat is being added to that ice, trying to make it melt, all of that heat energy is not going into making those particles move faster, meaning increasing kinetic energy. All of that heat is being added to shuffling the particles around, trying to break the forces of attraction between those particles, getting them ready for the phase change, meaning getting them ready to potentially change into the next phase. Okay, potential energy is the only thing that's changing here as heat is still being added to the system. Same thing if I have a pot of water that I put on a stove and make it boil. The second the first bubble starts to pop up, That will happen at 100 degrees Celsius. And y'all, until all of that water evaporates and turns into a gas, it will not increase its temperature above 100 degrees Celsius once it is fully transformed into the gas phase. Because at that point, at that phase change, all of the energy that's being added is going into potential energy of the particles trying to break their forces of attraction together, not kinetic energy. Look at this. This is so fun. Okay. Now, I'm talking about adding energy. Oh my gosh. Adding or absorbing energy. Oh my gosh. You guys, I can classify phase changes as either endothermic or exothermic because phase changes involve absorbing or releasing energy. So they can be classified as endothermic, absorb, exothermic, release. So we're going to go back to our heating diagram here. And you guys, all of those phase changes that go up my heating curve are going to be endothermic processes, okay? So they will be absorbing heat to undergo those phases, okay? So the solid to liquid to gas transitions, all of those phase changes are endothermic. They involve an absorption of heat to overcome the forces of attraction between particles. That makes sense. We know my solids, they like to stick close together, but if I add energy to them, they're going to spread apart and move faster. That means they will transform into the gas phase. So endothermic is going up my heating curve. Let's see, what do you think exothermic is? Y'all, it's going down my heating curve, okay? The gas to liquid to solid transition, any one of those phase changes are exothermic. These phase changes involve a release of heat to slow down the particles. And some of y'all are thinking, like, oh my gosh, but water vapor is super hot and ice is super cold. Yeah, because it has released its heat out of itself. So yeah, it's going to look cold when it's done because it has released all of its heat energy. Okay, so that is amazing. Y'all, all of these things can be classified as endo and exo. Chemical reactions can, physical just processes, and now we have phase changes. We got the endo and exo going on for us, which is amazing. Which, oh my gosh, if I'm saying endo and exo, you better believe I'm about to throw in some positives and negatives in here. Y'all, the amount of heat absorbed up a heating curve or released falling down a heating curve can be calculated by Q. So go ahead and add on your line going up showing endothermic processes absorbing heat. We know that endothermic is a positive Q. And on my line going down on my exothermic processes that release heat, exothermic will be a negative Q, and that indicates the release of energy. Oh my gosh, you're like, but the Q, does that mean we're gonna have to calculate Q? Well, yeah, we could. If you were my honors kids, you will be doing these calculations, okay? On-level kids will maybe pick a little small section of the graph and we'll run a couple of practices of using the Q equals MCAT equation. It will not be very tricky, but honors kids, we're going to have an entire day on really interpreting these heating curves. But what I'm looking at here is on my 5 different sections of my heating curve. I have a different Q equation to represent each. Please go ahead and write those Q equations on your graph in your notes now. During the phases, meaning during a solid phase, during a liquid phase, or during a gas phase, I just use my Q equals MCAT, okay? But during the solid to liquid transition, meaning the melting and freezing part, I use Q is equal to M delta H fusion. Okay, I'm going to get to that here in a second. Now, on my vaporizing and condensing part of the graph, I use Q is equal to M delta H of vaporization. Let's bounce on back to just talk about the solids, liquids, and gases, the ones that we know Q equals MCAT. This actually makes a lot of sense because we said the slopes are the only regions of the graph where temperature is changing. That's why it's able to slope up. Well, that's why I see the temperature change in there. I would not have a temperature change on a plateau because that does not exist, which is why you do not see the delta T part in there. But I do see a delta. I see a delta H of fusion and a delta H of vaporization. Well, let's technically... A heat of fusion is what the delta H of fusion is. And that's just the amount of energy needed to melt 1 gram of a substance, okay? The heat of vaporization is the delta H of vaporization that I see up here. And that's just the amount of energy needed to vaporize 1 gram of a substance. It's not a delta T, meaning a change in temperature. It's a delta H, which just means it's changing the energy content of the particles, which you will not see as a change in temperature, okay? It's just being stored into those particles, allowing them to get ready to change phase. So I can do some calculations with this, right? I can say, start with a sample of ice that is at -5 degrees Celsius. How much total energy would it take to become a gas at like 150 degrees Celsius? You can add all of those Q resulting equations together, and the total of that would be the total amount of heat, if I'm moving up the curve, absorbed to get those phase changes to happen, which is actually really cool that we can get some numerical values from this, yes? So that is amazing. We have done it, you guys. We have done phase changes. Let's watch a real cute, real sweet video, and then we're going to kind of summarize it, wrap it all up in a nice little package with a bow on top.
Welcome to Moo Moo Math and Science and endothermic and exothermic phase changes. Phase changes are physical changes that occur when a substance changes from one state of matter to another, such as a solid to a liquid or a liquid to a gas. Phase changes can be either endothermic or exothermic. An endothermic phase change is a phase change that absorbs heat from the surroundings. This means that the temperature of the surroundings will decrease as the substance undergoes the phase change. Examples of endothermic phase changes include melting, which is solid to liquid, vaporization, which is liquid to gas, and sublimation, where it goes directly from a solid to a gas. An exothermic phase change is a phase change that releases heat to the surrounding. This means that the temperature of the surroundings will increase as the substance undergoes the phase change. Examples of exothermic changes include freezing, which is liquid to solid, condensation, gas to liquid, and deposition, when it goes directly from a gas to a solid. A helpful way to remember the difference is as follows. Imagine you're sitting in a room with a window. Endothermic sounds like into, so warm air will flow into the room. As the warm air flows into the room, your temperature will increase. Exothermic sounds like exit, and again you're in the room and warm air will exit the room. And as warm air exits the room, your temperature will go down.
I love this energy unit because there's a lot of consistent, repeated things. Like we have seen endo and exo and release and absorb and positive and negative all over this place. But it's just a way for us to be able to explore the world around us in terms of energy changes that occur, which is really, really fun. So your heating curve has a lot of stuff that you have written on it, and it is all good stuff, okay? But the cool thing here with these Qs is we're still dealing with this. When Q is positive, energy is absorbed and the process is endothermic on a heating curve that looks like moving up a heating curve. When Q is negative, that means energy is released and the process is exothermic. So that would look like me moving down the heating curve. So yes, y'all, we can classify chemical reactions, physical changes, phase changes as all requiring either an absorption or a release of heat energy.